Well, good evening and welcome. I'm Jim Plummer, the Dean of the Engineering School, and we're here this evening to honor Bill Perry, who's a former U.S. Secretary of Defense and Professor Emeritus in our Management Science and Engineering Department. We're also delighted that Bill's wife, Lee, is with us, and Bill's daughter, Robin, are with us as well to celebrate this evening. Not only do we have a packed house here in the video auditorium, but there literally are hundreds of Stanford alums who are watching the live webcast of this event over the internet. The Stanford Engineering Heroes program is 3 years old now, and we set this program up to recognize the achievement of Stanford-affiliated people, faculty, graduates, and so on, who have profoundly changed and advanced the course of human, social, and economic progress through using engineering. Our engineering heroes really embody all that the School of Engineering stands for. The school stands for innovation, it stands for entrepreneurship, for leadership, and for world-class teaching and research. And as we hear from our heroes from time to time, they are the people who have really changed the world using these attributes. This year's heroes, in addition to Bill, include Jerry Yang and David Filo, who were the founders of Yahoo, John Bloom, who was one of the earthquake pioneers, and Marty Hellman, who was one of the people who invented public key cryptography. And these inductees this year include a distinguished group of inductees from the last couple of years, people like Fred Terman and Bill Hewlett, Dave Packard, and Vince Cerf. So it's a very distinguished group of people who have been affiliated with the engineering school and who really have, each in their own way, changed the world. So unlike many award events, we actually ask the people that we're honoring how they would like to spend some time at Stanford and try and set up a day or an evening or an afternoon that would really be special and meaningful to them. And Bill spent this afternoon, first he and I had lunch together with some engineering PhD students, and he spent the afternoon touring some engineering labs and seeing some of the interesting research going on, particularly I think in the area of energy, which is going to be a highlight of his talk this evening. So as all of you know, Bill is best known as the nation's 19th Secretary of Defense. He served under President Bill Clinton between 1994 and 1997. But he's also really widely recognized as a longtime advocate for the need to reduce the danger of nuclear weapons. And I think some of this traces back to the time when Bill was in the Army Corps of Engineers, and he served in the Army of Occupation in Japan, where he saw firsthand the devastating effects of nuclear war. He's one of those unique people whose career has spanned public service, business, and academia. And if you look through his career, you will see him actually moving from one to the other and then back and forth through the time that he's spent in Washington, at universities, and in industry. He's been decorated by more than a dozen countries for his work, including the U.S. Presidential Medal of Freedom. Bill is currently an emeritus professor in our Department of Management Science and Engineering and a senior fellow at the Freeman Spogli Institute. But his association with Stanford actually started more than 60 years ago when he got a bachelor's and a master's degree here in mathematics. And then he returned back here in 1989 as a faculty member. So as I said a moment ago, he's really spent a career kind of straddling industry and government. And after he completed his PhD at Penn State, he took a job in the defense industry and was also a technical advisor to the Defense Department. So the story he tells about this is that in one day in the fall of 1962, he got a call to go to Washington to consult on what was described as an urgent technical problem. So when he arrived, apparently he was shown some pictures of some Soviet missiles being deployed in Cuba. And I think this was really a stark introduction to some of the geopolitical problems that Bill spent much of his career on later. In 1977, he became Undersecretary of Defense for Research and Engineering under Jimmy Carter. And after that term, after Carter's term, he returned to the Bay Area, but stayed very active in national politics. He returned to Washington as Secretary of Defense in 1994. One of the hallmarks, I think, of Bill's tenure as Secretary of Defense was that he did what he could to reduce the Cold War's deadly legacy of nuclear weapons. And in 2007, he took a really dramatic step by joining forces with former Secretaries of State George Shultz and Henry Kissinger and former Senator Sam Nunn to publicly call the world's attention to the grave danger posed by nuclear weapons. And he's been a tireless campaigner for this cause since that time, well, in fact, for all of his career. So in addition to his many honors, he's a member of the National Academy of Engineering, the American Academy of Arts and Sciences, and he's been recognized for distinguished services by almost every agency associated with the Department of Defense, NASA, and so on. And he's even, in 1988, was named a Knight Commander of the British Empire. So tonight, Bill, we celebrate you as an engineering hero, and we're going to present to you, you can let it sit here for the moment, but this is a copy of the plaque which is on the wall just outside to the right, where we have wall plaques of all of the engineering heroes. So please join me in welcoming the latest engineering hero, Bill Perry.
Introduction. Can you hear me in the back? I really feel a little sheepish standing up here because while I have 2 degrees from Stanford, I never took an engineering course here. But all of my degrees are in fact in mathematics. But as soon as I graduated, as soon as I got my PhD, I went to work for an electronics company and stayed there for about 10 years and then founded my own electronic company and left there only to become the Director of Defense Research and Engineering, which was sort of being the chief engineer of the country. So I think that maybe makes me feel all right about standing up here in this engineering environment. Most of my time, as Jim has suggested, has been spent working trying to reduce the danger of nuclear weapons, and in particular, doing everything I can to ensure that a nuclear weapon is never, ever used again. And most of my talks, in fact, are on that subject. But I decided to deviate from that tonight. First of all, it is a depressing subject, really. And I get depressed sometimes talking about it, as important as it is. And I wanted to have a more hopeful talk tonight and decided to talk about energy, which is a very important subject in which we have made remarkable progress, primarily because of technology developments, many of them happening right here at Stanford. I have tied the subject of security. My title is Energy, Technology, and Security. So why do I tie it to security? Every American president, going all the way back to Dwight Eisenhower, have stated that an increased dependence on foreign oil threatens our security. Every president promised to break that dependence. Eisenhower said that if more than 20% of our oil had to be imported, it would endanger our security. President Nixon promised energy independence by 1980, which is some time ago, you know. Carter called energy crisis the moral equivalent of war. Clinton said that energy is a key to our national security. And President Bush, the second President Bush, lamented America's addiction to oil. So when I say that this is a security problem, I'm in good company. All of these presidents have said that. There's been a bipartisan consensus for these last 60 years to reduce our dependence on foreign oil. Well, all presidents for the last 60 years have promised to do so. How well have they done on their promises? Just 2 figures to put this in perspective. In 1970, our oil imports were $3 billion. Last year, they were more than $300 billion. So if I were a professor grading our presidents on that particular promise, I think I would give them an F. How has this failure affected our economy? Well, oil imports account for about 2/3 of our trade deficit, 2/3 of the trade deficit. Trade imbalance is certainly an economic problem, but it is also a national security problem. When you consider where this money is going, who is getting all the dollars from sales of oil? Well, it's Saudi Arabia, Russia, Iran, and Venezuela. Not exactly the list of the countries most friendly to the United States. In sum, oil dependence is both an economic and a security problem, just as President Eisenhower and the other presidents have said. So why haven't we been able to solve this problem? The answer is pretty simple. Solutions take money, and that spending has to be sustained over a long period of time. In particular, the solution that requires development of new technologies, and that has been dramatically underfunded. And it takes decades of funding to reach the scale to make it that has any real significance to it. I'm going to give you a few facts from a National Academy of Engineering report to make my point here. The U.S. budget, when this report was written a few years ago, was about $4 trillion. Out of that $4 trillion, health ate up 22% of it. My old friends in the Defense Department ate up 20% of it. Energy was substantially less than 1% of it. If we look just at the R&D, the DoD R&D that year was $77 billion. Health R&D was $28 billion. Energy R&D, substantially less than $1 billion. So that indicates the government's lack of priority on this subject. Spending on energy R&D hit a high in the 1970s when we had a big oil crisis and people were standing in line to get their pumps filled up. So it was higher actually in the 70s than it is today. Now, people have said, well, you're giving government figures. This is a problem that market forces will solve. Some of my really good friends in the business department lecture me on this is a problem which market forces can solve. So let's take a look at how effective the market forces have been in solving this problem. The pharmaceutical industry spends 18% of its sales on R&D. Even the stodgy automobile industry spends 2% of its sales on R&D. The energy industry spends 1/3 of 1% on R&D. So much for market forces. Now, I'm a great believer actually in market forces, but I have observed that the executives are averse to what I would call delayed gratification. In other words, if the R&D investments take 10 or 15 years to really pay off, they don't want to make them. If they can see a payoff in 2 or 3 years, they're more interested. The problems we're talking about require long-term, sustained investment, and that is not happening. Okay, that's the bad news. Now let's take a little bit look at the good news, because there is some good news. I told you I was going to give you a hopeful story tonight, and there is some good news here. Beginning in 2009, the figures I quoted you from 2008, in 2009 it started to turn around. Most notably, Steve Chu, who's now Professor Steve Chu, created something called ARPA-E, Advanced Research Project Agency-Energy. Obviously, he was emulating the Defense Department's ARPA. But other agencies in the government have tried to emulate ARPA unsuccessfully. This time, it was successful. And that's one bit of hopeful news here, is we now have in our government an agency which is promoting energy R&D and promoting it very successfully. But that's R&D. You still have to get the developments up to scale, which is a big task. The Department of Energy has used several $billion of the stimulus funds several years ago to underwrite new industrial manufacturing plants for solar systems to accelerate the date by which those will become cost competitive. They are not batting 1,000 on that, I must say, but they're doing pretty well. So people in the press tend to look at the one major failure. They're overlooking the fact that several other of these investments have indeed been quite successful. As a result of these Department of Energy initiatives, as well as several very important developments in industry, the goal of energy independence is now in sight, literally and really. I believe that before the Stanford students that I talked to today. I believe that before I talked to them today, but I believe it even more after that. I spent the afternoon touring some of the R&D laboratories here at Stanford, 2 of them working in very fundamental issues in the energy field. I would say this: I think that by the time the freshmen who entered Stanford this year graduate, we will have what I would call energy independence. But let me be more explicit what I mean by that. It doesn't mean we won't be buying oil from anybody. What it means is that if you pull together North America, United States, Canada, and Mexico, then I think by that time, by the time these kids graduate, we will be net exporters of energy, net exporters. This will be, if it happens, will be a major plus to our security. It will cause a major improvement in our trade balance, and it will be a beginning in the decrease of CO2 emissions. Just a beginning, because some of the things that allow us to do this are still involve gas and oil. I'll say more about that. But these early improvements result from an increased oil production from Canada's tar sands, increased production from Mexico as Pemex, which is a nationalized oil company in Mexico, and for years has resisted using technologies from other countries, is now beginning to turn around and starting to use the best technologies from Canada and the best technologies from the United States. And that's going to lead to an increased production in Mexico. But these improvements initially only going to make a small impact on our CO2 emissions. Major improvements depend on technologies already underway, some of them already developed, but not yet at scale. It has to be at scale to make a difference here. In a sense, we can think of the major production of gas and oil that's come along, that may be brought about by the fracking techniques, as giving us a 10-year grace period to bring up to scale the emerging sustainable technologies. So in the long term, we have to get to these emerging sustainable technologies. But in the meantime, we do have this increase in gas, we have the increase in oil. We should not look at that as a solution to the problem, but as a 10-year grace period. Let's talk about some of these. The electric car. The electric car has a great potential to reduce the demand from fuel. But all electric cars use no fuel. They're economical in the use of electricity. Plug-in hybrids, of which I own one, I'm getting about 100 miles to the gallon, which isn't bad. And the regular hybrids are getting 40 to 50 miles to the gallon. So that sounds great. And I would also say, and by the way, there are more than 1 million cars of these type in the United States today. And 1 million sounds wonderful until you stop to compare it with the 249 million that are not hybrid. So we are less than 0.5% of the cars in the United States. So we're along, that's what I mean by not being at scale. To get up to a meaningful scale, 2 things have to happen. The price has to go down, and the range has to go up. And what that's going to entail is battery R&D. And I'm happy to report to you today that battery R&D at Stanford is one of the world's leaders in battery R&D today. And in my tour of the laboratories today, I saw some work being done in batteries here. This absolutely blew my socks off. Very exciting. And it's not commercial yet, but it's very close to being ready to be made commercial. So my confidence is high that these new developments will be in production in a few years and at a scale, a significant scale, well before this 10-year grace period window that I talked about. Perhaps the long-term sustainable technology is solar. One of the obvious drawbacks to solar is that it is not yet cost competitive on the grid. Today, I would estimate that electricity coming from solar on the grid is probably about 1%. So it is not at scale, not close to being at scale. The problem in getting it introduced to a larger extent, I would say it's primarily a learning curve problem. Solar today is on a 22% learning curve. So each year they get down about 22% in cost. And that's good. But it's going to take them a good many years to get down to the really, truly cost competitive. In the meantime, it's a moving target because the cost of natural gas is going down, and therefore you can generate electricity from natural gas, and that cost is going down. Another problem with solar reaching scale is that it fundamentally is limited to when the sun's out. So there's only so many hours per day you can have it. And people like to turn on the lights or plug in the utilities in the nighttime as well as the daytime. So you have to way of dealing with that problem. The problem would be low cost, high capacity storage, which is so far the holy grail which has eluded the world. Today at Stanford, I saw a novel technique which leads me to believe that a solution to that problem may very well be in sight. I'm not going to say anything more about it, but for the first time, I developed some optimism on that problem. Much work has been done on biofuel. Brazil is in large-scale production of ethanol from sugar. The last I heard, the majority of the fuel being used to power cars and gas in Brazil comes from ethanol made from the sugar. And modest quantities of ethanol are being made in the United States from corn. I have to say that I do not believe either of those have any real sustainability, fundamentally because they're using a valuable and expensive product as the feedstock. You're never going to get the cost of ethanol made from corn down to a reasonable price because of the fundamental value of the feedstock which goes into it. The needed development is biofuel using a low-cost or a no-cost feedstock. The most obviously used example, instead of doing it with corn, you do it with corn cobs or corn stalks, which surprisingly have a lot of sugar in them, but the sugar is locked up inside the plant. It's made it very difficult to get it out. I have seen very, very promising developments in biofuel using cellulosic material, using corn cobs, corn stalks, that I believe could be operating at a significant scale in 5 to 10 years. So that falls within my 10-year window also. If realized, that could be a very significant step in meeting this window. But it is clear, besides increased supplies, we really have to start working on reducing demand. You cannot separate these two issues. The global automobile industry, stimulated by the American government's establishment of what's called CAFE standards, is really making amazing strides in that direction. I can remember when the government first started putting standards of miles per gallon on the automobile company. I remember attending a meeting of the National Academy of Engineers where the chief engineer of General Motors stood up and said, "This cannot be done. This will just drive the cost or drive the complexity of the cars completely out of the window." I heard that speech about emissions from automobiles, and I've heard that speech about getting the miles per gallon up. Well, it is working, and it is happening. We've made dramatic improvements in efficiencies this past decade, and even more dramatic improvements are coming. The NAE has completed a study on how fuel-efficient cars will grow in importance in the next 2 decades. And this study concludes that in a decade, or 1 decade, about 50% of new cars sold will be designed substantially, their word is substantially more efficient than present cars. These improvements have already started to take hold. And of course, I mentioned already the hybrids and the plug-in hybrids and the electric cars that contribute to that. If you put all of these together, CAFE standards have actually led to a 13 million gallon decrease in gasoline consumption this past year. The first year in history that I can remember where the consumption of gasoline, instead of continuing up, has started to go down again. It's a small amount down. 13 million gallons is not very much compared to how much we use, but it is going in the right direction. The favorable trend could be accelerated if the cost of plug-ins and the cost of electric cars could be brought down. to more competitive prices. And that depends on significant improvements in battery efficiency, which I've already discussed. So Stanford here is working absolutely at the frontiers of two technologies which are vital to this problem. One of them is the long-term batteries for long-term storage, for storing solar energy on the grid, and the other is batteries which will be much more efficient for automobiles. So I have two bottom lines for transportation. The first is that car efficiencies have more than offset the increased demand, and the next 5 years will lead to a continuing decrease in gas consumption. So we're certainly moving in the right direction there. And secondly, cellulosic biomass could begin to be a substitute fuel in 5 years and be up to a significant scale in 10 years. So my optimism in the transportation field depends on those two factors: the rapid scale up of biofuel and continued improvements in bioefficiencies. All of these research areas, Stanford is a pioneer and a leader in the field. But of course, as electric cars and plug-in hybrids drive up fuel efficiencies, there will be a concomitant increase in the demand for electricity. Electricity does not come free. So I'm going to start a little bit about some facts, what I consider facts about electricity. In some industrial nations, nuclear power is the primary source of electricity. Korea is one example. France is another example. It used to be true of Japan, not so much anymore. Other nations, China and India, have indicated they plan to turn to nuclear power in the near future as a major source of electricity. Both China and India are talking about buying 50 more reactors, for example, in the next decade. The good news is that if this occurs, it would lead to a decreased global emissions of CO2. But there's some bad news too. The bad news is that it could substantially complicate the global efforts to control nuclear weapon proliferation. Without going into any detail to that, just to remind you that the fuel that you make to put into a reactor, you have to enrich uranium up to about 5% to make the reactor work. But if you have a device for enriching uranium to 5%, you can also enrich it to 90%, which, by the way, is what we use when we make nuclear bombs. So that is why we have an issue with nuclear power, not because of the reactors or the electricity they produce, but because the fuel that they use is susceptible to being converted, or the systems that make the fuels can be susceptible to make fuel for weapons as well. The most obvious example of this proliferation problem is North Korea, which for 2 decades had what they advertised as a commercial electric power generating reactor until they threw the UN inspectors out and started generating plutonium that can be used in nuclear bombs. They now have 6 or 7 nuclear bombs as a result of that reactor. So that's how they got their nuclear bombs, by a commercial, what was advertised as a commercial program, which turned out not to be that at all. And Iran may be following in the footsteps of North Korea. I must say I am somewhat encouraged by the speech made at the United Nations last week by the new president of Iran. And I take him at his word. He did not have the final decision about what happens there. The final decision is by the supreme leader. But so far, I think this is encouraging enough that I'm encouraging our government to take it seriously and to sit down and seriously discuss, negotiate with Iran, because the alternatives are so grim. A nuclear Iran will lead to a proliferation, not just in Iran, but in the whole Middle East area. And this is one of the most explosive areas in the world. And to find those countries which find some reasons for fighting with each other about once a year, now we have nuclear weapons among those countries, we're really asking for catastrophe. Getting back to nuclear power, I have just remind you that the United States has more nuclear power, more nuclear reactors than any country in the world today. But after the 3 Mile Island accident, we stopped building reactors. And today we're still operating over 100 reactors, but more than half of these are over 30 years old and are in life extension programs as we speak tonight. With the aging of our nuclear reactors and the growing concern of global climate change, the United States reconsidered its self-imposed moratorium on nuclear power, and several new permits were granted a few years ago. Many in the United States talked about a nuclear renaissance, but in the wake of Fukushima, that talk has died down. And at the moment, there are only 2 nuclear reactors being built, and it's not completely certain that those 2 will ever go into operation. So I think we're sort of back on the self-imposed moratorium on nuclear power. In the meantime, we are generating 40% of our electricity from coal plants. And nothing can be more destructive to our environment over the long term than coal-generated electricity. The somewhat good news there is that 5 years ago, it was 55% of electricity. Now it's down to 40%. More and more of these plants are being shut down. And in the same period, we have almost completely eliminated generation of electricity from oil. So that's the good news from a carbon dioxide point of view. The bad news is one of the other major sources, hydro, has been stuck at 15% almost forever, and I see no prospect of us getting significantly more hydro energy. And nuclear power, as I've just suggested to you, is probably on the way down and not on the way up. And after all the years of effort and public attention, only 1% of our electricity comes from solar, 1%. So it's a marvelous technology, but it's very, very far from being at scale. Now, those are the facts. Let me offer you some opinions about what we should do about that. I believe we should make it a national priority to replace coal plants as soon as possible. They are one of our major contributors to carbon dioxide. Incidentally, I might say, even if we do that, how do we influence China to do the same thing? They are now building 2 coal plant reactors per week. It's just, and they understand the problem. They also understand that they want their economy to continue to grow. And until they get their nuclear plants online, they'll continue to do that. So the only hope of China's CO2 emissions starting to go down again is, by the way, through these nuclear plants that they are planning to build, but which are at least 3, 4, 5 years from being operational. So I say we must replace all of the coal plants in the United States, and we can do that. The new hydro is very unlikely. There's never going to be another Three Gorges project in the United States. Solar and wind will eventually become significant, but will be very slow to reach significant operational stage. And nuclear, I believe, is not going to be the solution. I actually favor the reactors, but I just have to say I do not think it is going to happen. We have very good potential in reducing our electricity demand through efficiencies, which we are moving, I sort of say, very slowly at. Here, the technology is already available that could save perhaps 20, 30, 40% of the electricity used in commercial industrial buildings and in houses. And the cost of making those changes is such that payback periods of the cost are in the order of 3 or 4 years, which is reasonably attractive. But in spite of that, nothing is happening. I should say very little is happening in that direction. We see demonstration projects, we see showcases, but in terms of it making a real effect, not very much is happening. And I strongly believe that we must move much more vigorously on that front. The simple things like light bulbs, efficient design of houses, efficient office buildings, they're already underway. They have great potential, but we're only scratching the surface now of what we could do in that area. Over the next 2 decades, it's estimated there will be about a 1/3 increase in electricity demand as our population and economy grow, and especially as the number of electric and plug-in cars increase. But if we continue to pursue building efficiencies aggressively, we should be able to offset the increase in energy demand with increased efficiency. We can at least hold even in that area. But how do we do better than just holding even? How can we actually move forward in this area? The alternative fuels, solar, wind, are developed, still too expensive to get much of a use. I believe it'll probably take 5 years to get the cost down to grid parity, that is cost competitive with other sources. So we have 5 years, and that's why I look for this grace period of using other technologies in the meantime. It's going to take 10 to 20 years for alternative fuels to go from 1% to maybe 10%. 10% is not a lot, but it's a lot better than 1% and moving in the right direction. In sum, alternative fuels are potentially important, but still small and will be slow to play a significant role. Part of our national policy should be to accelerate that. Part of the national policy designed by both the former Secretary of Energy and the present Secretary of Energy are to do just that. We've talked already about why solar is so slow to compete. It's called a learning curve, and we have to do better on that. And accelerating the production is so it's a chicken and egg problem, really. We don't have enough demand for it because it's too expensive. We can't get the cost decreased until we get more demand for it. That is probably, in my judgment, a role for government to play to try to stimulate that demand and try to accelerate the path down the learning curve. The learning curve helps explain why solar and other renewables are so slow to be competitive. And that's why we have this chicken and egg problem, and that's why when Steve Chu was Secretary of Energy, he did undertake a government program to try to accelerate the path down the learning curve. And any of those of you here in this audience that would like to criticize him for taking those moves, I will be glad to debate that with you. Without doubt, the biggest game changer in the United States in the generation of electricity has been the aggressive development of shale gas by the industry. This is a technology that goes back 10 or 20 years, really, but it's just hitting us now with an impact we can feel. There's a huge supply of shale gas in the United States. The conservative estimates are it's enough for more than 100-year supply for the United States. The technology is mature. The so-called fracking drilling process was developed more than 10 years ago, and the success of it has exceeded everybody's expectations. It's already at scale. We already have gone from a net importer of natural gas to a net exporter. The plants and ports we were building for exporting natural gas overseas are now being converted to export natural gas overseas. And it's demonstrated to be cost effective. I want to digress a little bit from the energy to talking about one of the consequences, in particular of this shale gas revolution. It has made for the United States manufacturing plants, it has given them an advantage in fuel costs. Some plants that's important, some plants not quite so important, but for all plants it has some importance. And that, together with the introduction of robotic techniques in manufacturing, we're beginning to see a return of manufacturing to the United States. I was at a plant in Newark just last week where those combination, robotic manufacturing and the very low cost of energy we're facing, has now made the plant CEO is not even considering moving it offshore for the manufacturing. Now that is an important trend which we ought to do everything we could to try to encourage. The revolution in shale gas, of course, is not just in the United States. Shale gas deposits have been identified in Eastern European countries, Poland and Ukraine in particular, and China. And the revolution extends to shale oil as well, which is just now being developed in several states, and most in the United States, and also, most importantly, in Canada. All of these are factors which are leading me to say we are going to energy independence, not in some imaginary 50 years or 20 years from now. It's going to happen in a few years, as I said, before the students who are freshmen here today graduated. So what is a plausible strategy to promote the best of this and to hold back the worst of it? We have to continue to push on efficiencies efficiency, everybody talks about building the supply up. Bringing the demand down has the same effect, even a better effect. And we have a minimum goal in that should be offsetting the increased demand. That's happening today in electricity for housing. We should have a high priority for the United States natural gas to replace the remaining use of oil in electricity generation. And as alternative fuels come to scale, gradually replace the coal-fired plants. This is a viable plan, but it will kick in slowly because the long time for solar and wind power to reach a significant scale. How could we accelerate that somewhat? Could we do it by building a new generation of nuclear plants, for example? This is already happening in China and India. I do think it's not going to happen in the United States. There is one possible alternative to that. There's been developed recently something called a s'more. That's not something you eat in a campfire. This is a small modular reactor. And the DOE is planning to jumpstart s'mores by providing funding for the first 1 or 2 s'mores. That might bring nuclear energy back to the United States. It would be a blessing for 2 respects. First of all, because of the fact that it generates electricity with essentially no CO2 emission. And secondly, if we are again become technical leaders in nuclear reactors, this puts us in a much better position to influence what other countries do with the reactors, particularly relative to the subject of nuclear proliferation. If we do not succeed in doing that, and I would say that's more likely what will happen, we will not do it, then our plan should be to gradually replace the coal-fired plants with natural gas. Natural gas still has emissions, but they're about half of the coal emissions, so it's a step in the right direction anyway. This would lead to a major decrease in carbon dioxide emissions in the United States and worldwide. At the same time, it would lead to a substantial increase in energy security for the United States. As these same processes and technologies are introduced globally, they will lead to decreased oil prices and decreased coercive power of OPEC. Well, I'm going to conclude now. I've given you somewhat of an optimistic forecast. So it's only fair to ask, what could go wrong? And while I'm asking that, I want to also ask, what could go right? So I'm going to balance that with I'm going to start off with what could go wrong. You might say the crows here. What could go wrong? Well, first of all, environmental concerns could decrease or stop shale drilling. It's already a big political issue in Pennsylvania, my home state, where there's lots of shale gas. They're already drilling for it, but lots of resistance because of both real and alleged problems of environmental issues. I guess the only comment I would make about that, and I actually helped write a DOE report on the subject a few years ago, is that both the government and the industry should be very, very sensitive to what would happen if we had a 3-mile island incident in fracking. Something, environmental disaster happened in fracking, which really turned the public off on the subject and put on huge pressures to stop the fracking. It would be catastrophic for our energy supply. It would be catastrophic for all of the forecasts I make. It could happen. Part of what the report says, it need not happen. We know what the issues are. We know what to do to prevent them. It does take careful attention to detail by the people drilling and careful attention to detail by the regulators. The complication here is that regulation in this field is not very much at the federal level. It's at the state level. And every state, as you might imagine, has a different set of rules for how to do this. And some of them, and more importantly, they have a different set of attention to detail in enforcing the regulations they have. But I think it's quite clear to me that a 3-mile island incident in fracking could be a catastrophe for the industry. Secondly, what could go wrong, the plug-in hybrid costs could remain too high for general usage. I bought a plug-in Prius, but I never deluded myself that it was an economic decision I was making. I've gone through the calculations a couple of times. It does not really pay for itself, except perhaps over 10 years or some long period of time. The assumptions you have to make this an economic issue are not really quite plausible. So you have to, and so most people are going to make the economic calculation. We have to get the costs down for this to happen, and it might not happen. The third thing that could go wrong is the cellulosic fuel, which I was pinning some of my hopes on here, could fall into what venture capitalists call the valley of death. There's the technology is here now, not in production yet, and getting from here to there is a tough problem. It goes through a little valley, which I say they call the valley of death. That's happened to a lot of otherwise pretty good technologies. And if that happens, we'll never get the cost low enough to get cellulosic fuel up to scale. So that would drop off my plan. And finally, we could, and we probably will, lack the political will to carry out hard programs like the small modular reactors. So those are the pros. Those are the things that could go wrong. But let me talk a little bit about what could go right, which I'll call the bluebirds. Where are the bluebirds out here? What could happen better than what I'm talking about? First of all, we could reach grid parity with solar sooner than I have projected. The renewables could provide 20% of the electricity 10 years from now instead of 10%. It takes a lot of good things to happen. That was the direction Steve Chu was trying to move the Department of Energy through his program to stimulate production plants to come up. We'll have to see now what the new Secretary of Energy wants to do about that. But if he takes the same aggressive approach to getting the cost of solar down, then we could get grid parity much sooner than that we're now planning. Secondly, we could make a battery breakthrough. And it could happen right here at Stanford. In fact, if I had to bet upon it, I bet it will happen right here at Stanford. And electric cars could become a significant market much sooner than forecast. I have high hopes for that to actually happen. We could use natural gas for transportation instead of gasoline or diesel fuel. Even today, some of the bigger trucks are making the costs of modifying their engines and putting the storage tanks for the natural gas in, and they have a payback period of about 2 to 3 years, which isn't bad. If we get a little improvement in costs and modification costs, for example, we might see all trucks on the road operating on natural gas. That would be a good thing, I think. Our government, fourth one is our government could really, really surprise me and adopt a carbon pricing policy. That would have a profound positive effect on all this. All the decisions that people would have to make would now be based on economics. And if you put the economics into the picture, many of the things we're doing don't make sense at all. And if they had to actually pay the costs for what building a coal-fired electricity plant means, the full cost of it, then coal doesn't seem so economical or so attractive anymore. My forecast did not assume any of these bluebirds. And I'd like to end this talk then on a high note. And that is, on balance, I believe that the bluebirds are more likely than the crows. Thank you.
So we have a little time for questions. We don't have microphones. Oh, we do have microphones, yeah. So if you'd like to ask a question, we'll get the microphone to you right here.
Hi, excellent talk. I didn't hear you mention anything about nuclear fusion. Do you have any comments about that?
Is that microphone on?
Mike is not on.
Yeah, the question was about nuclear fusion. Do you have any opinion on fusion?
Yes.
Nuclear fusion.
Would you share it with us?
Would you like to hear it? The joke is that nuclear fusion is the energy source for the future and always will be. I don't share that view. I, for many years, was on the technical advisory board of the Livermore Laboratory. They have had a fusion program underway there for many years. They have passed a very important landmark just a few months ago. All of the lasers, these are very high-powered lasers, a couple hundred of them, all focusing their energy on one little bitty spot. And it's working very, very well. Having said that, they have not yet achieved fusion. My foolish forecast is that's going to happen within the next year, in the year 2014. If that happens, then everybody's going to start getting serious about making less electricity with fusion. As it is, the laboratory is already using this facility in their nuclear stockpile stewardship program, and have done very important research programs from it. But it could be used for general electricity. I have to say that that's probably, after they hit the fusion, it's probably another 20 years before we see it. So it's not in my 10-year time frame, but it's something that we want to consider for the future. The investments we've made on it so far have been, I think, a good investment.
Marty?
Another bluebird would be if the United States were to get the soft cost of solar installation down. I heard our colleague, former colleague Dick Swanson talk on this, and I thought he said it costs 4 times as much to install solar in this country as Germany, but I may be getting it wrong. I Googled it during your talk, and it was a number at least a factor of 2.
I can't comment on the numbers you're using, but I agree entirely with the point you're making, that a big part, whether it's 3 to or 4 to, a big part of using solar energy, for a house using solar energy, having on the roof, say, is the cost of installation and maintenance. And if we can make a big reduction in that cost, along with going down the learning curve on the first unit, we might get to a competitive nature in solar sooner than people are now expecting. And there could be and if we hit that point, there could be a landslide movement of people moving in that direction. It could happen much faster than you would expect, because the manufacturing capacity would build up very quickly and very easily to do that. Yeah.
Mm-hmm. Yeah. Question back there.
Hi, yes. I live in LA, and I actually drive by the oil refinery plants in the South Bay area. And across the street from the oil plants is the single hydrogen fueling station. Do you have any comment about hydrogen fuel cell technologies?
Yes. I'm a big fan of fuel cells. There's a company just down the road here called Bloom Energy, which makes what I think are the best fuel cells being made in the world today. I, for many years, was an advisor to United Technology Corporation, which has a fuel cells division. And this company, Bloom, is just done much better than the company I was involved with by going to a different technology. It's called solid oxide technology of fuel cell. And they're now selling their fuel cells to companies like Google and Apple as a fundamental electricity source, not just being there as a backup to the grid, but replacing the grid. And it turns out to be about a break-even proposition today. Every reason to expect it will be much more attractive than that in the future. So I think but still, fuel cells have to be fueled by something. Where do they get the hydrogen? They get it from natural gas. So one of the reasons fuel cells I think will become more attractive in the future is that natural gas costs are going down. It's the one energy system I can think of where costs are actually going significantly down.
Mm-hmm. Question?
Where do we stand in storage of spent fuel and nuclear fuel? That's always been part of the discussion.
It's a technically easy problem, a politically impossible problem. One thing what we're doing is just putting them in caskets and burying them underground. And that's okay. I mean, that works all right. But after a while, you begin to run out of time on that process. I believe the long-term solution is probably developing reactors that can get rid of the bad stuff in the spent fuel. That's not anywhere near happening today. As far as I know, nobody's working very hard on it. But that is a long-term solution to the problem. And it is a long-term problem. We can deal with it short-term, 50 years, 100 years maybe, by just doing what we're doing now.
Mm-hmm. Dave?
Yeah, Bill, you're a political expert as well as a technical expert.
I deny that, but go ahead.
Say a few words about your view of the likelihood getting full cost applied to consumables like oil, especially if other costs are going down, which gives maybe an excuse not to.
My uninformed political judgment is that I cannot conceive of the situation when the United States Congress will do anything that's sensible. I'm sorry to say that. And I'm not trying to make a general statement about the Congress, just on this issue. On this issue, they have shown that they won't even consider raising the tax on gasoline, for example. And that's just stupid. That would be one way of bringing the costs up to the more real cost. A better way would be to have a carbon pricing policy. And for a while, I thought there was some prospect that was going to happen. People from both parties were supporting it. When it actually got into the Congress, it became a partisan political issue and it just died. And given the performance of Congress the last 2 weeks, I don't see any reason to be optimistic about that getting improved.
It's a question way in the back.
I think that the president, if he chose to, could issue an executive order tomorrow to require all new federal purchases of vehicles to be powered by natural gas. Would you favor that if that is in fact possible?
I'm not a federal legal expert, but I believe the answer to that question is yes, and I believe it would be a good thing. One of the things the government could do, one of the things Steve Chu was doing when he was Secretary of Energy, was setting up the government as an example. I was talking about the slow adoption of efficiencies in buildings with them. Well, the government has a lot of buildings, and so he was trying to get the various agencies in the government inspired to do that, and some of them actually went along with them, many did not. But that would be one thing to do, and the executive order you're talking about would be another thing. One of the things I was suggesting for many years was for the Defense Department to convert their Humvees to hybrid cars. If you think your car is a gas guzzler, you should drive a Humvee sometime. But that never happened, and I don't think it's going to happen.
Yeah. Question?
Yeah, you pointed out something very interesting, that both in absolute terms...
Oh, excuse me, can I make just one other point on the last one, and then we'll come back to you. The fundamental problem of why that probably is not going to happen is that the economics of buying something like that requires a payback of so many years. And most industrial companies can make that calculation and make a decision based on that. But the federal government isn't funded that way. It's a year-to-year funding. And there's no incentive for one administration to pay a lot of their money, use a lot of their resources to make the next administration look good. So it's
Interesting. Yes, question?
Yeah, you pointed out the very real issue that both in terms of absolute dollars and relative percentage dollars, that research, both basic and applied, from the government funding standpoint and particularly from the industrial funding standpoint, is far lower on energy research than, say, health research or aerospace research. Without going into a huge number of details as to why that's true, are there any foreseeable actions that could occur to help remedy that?
Well, the figures I quoted were from 2008, and the R&D spending did go up pretty significantly during the 4 years that Steve Chu was Secretary of Energy. I would bet that they're going to continue to go up under his successor, who has been a big advocate of energy R&D for as long as I've known him. So I think, yes, I'm optimistic that the R&D spending by the government will go up. The problem with the R&D spending by industry is the one I'd mentioned. It takes so long to get the payoff on most of the things you're talking about. And companies do this payback calculation, but they start to get very woozy about the results when the payback period takes 5 or 6 or 7 or 8 years.
But that's what it takes in the drug industry.
Yeah, that's
It
right.
takes longer than that in the drug industry.
That's right. It does take longer than that, but the modality is different. You have all these bright startup companies located all around the Bay Area here who get venture capital money to start up, and they get to the place where they've actually got the drug through the second phase or the third phase of testing. And if that looks promising enough, then one of the big companies who's been spending nothing on R&D jumps in and buys that company. That seems to be the way the industry has dealt with the R&D problem. It's coming from venture capitalists who are supporting these companies, because the companies that make it, that actually get a marketable drug, that's a big bonanza for them. And so the big companies, the Squibbs and the Roches and so on, let most of their R&D be done by small companies who get the funding from venture capitalists.
Interesting. Question?
I'd like to come back to the nuclear question for a moment. You touched upon nuclear as an interim energy source between what we have now and many years from now when hopefully renewables will scale.
Did you get it, Jim?
Thank you. Can you hear me? Speak up.
Sorry. I wanted to come back to nuclear for a moment. You touched on nuclear as an interim technology between now and sort of a time when renewables have scaled. Do you see a space for breeder reactor technology at all in this? And do you think there's potential both politically and technologically for that in the next 50 years, say?
You get that, Jim?
For nuclear reactor.
For nuclear breeder reactors, which have been researched somewhat in Canada and India and a few other countries, but
I don't think I'm fully qualified to give you an informed answer on that question. My answer would be no. But I don't like to offer opinions on subjects I don't know a lot about. So.
Mm-hmm. Yes, right here.
Yes, I've heard the idea of thorium reactors being bandied around, and some people think they're wonderful. We developed one, I believe, years ago,
Yeah.
and now other countries are using them. What is holding that up if that isn't valid?
The honest answer is I don't know, but I have asked that question to our laboratory directors, none of whom show any enthusiasm for going to thorium, and I can't explain to you why. But I can tell you as a fact that there's not much enthusiasm going to thorium reactors in the United States, but I can't tell you why.
Question in the back.
Government initiatives like carbon tax, what impact do you think we as consumers can have in shifting our spending to, say, companies, to purchasing product from companies that do invest or use renewable energy?
So in the absence of a carbon tax?
We as consumers, can we influence, make an influence by shifting our spend to purchasing products from companies that do use renewable energy?
Can consumers do anything by purchasing products from companies that are more susceptible?
In manufacturing and such.
I think that's certainly a possibility. I'd hate to make a forecast on that. I come from a department, the Management, Science, and Engineering Department, which is well represented here tonight. A former department head, Elizabeth Pate-Canals over there. And the department specialized in how do you make decisions on complex problems in a quantitative and analytical way. If we had a carbon tax, this would drive people to make rational decisions about things we do, about things involving energy. In the absence of a carbon tax, we get a bargain when we get gasoline at $4 a gallon. We grumble about it being $4 a gallon, but it's a bargain because we're not counting all the incidental costs associated with it, including the environmental costs. So instead of trying to have the government tell everybody what to do, it would be much better if we had a carbon tax policy and let everybody decide themselves what to do, but based on a full deck of cards, not based on just partial information. But could we put pressure on companies and the government to do things by being selective in our buying? And it has worked in some cases. I have a hard time imagining it working in a case as big and as comprehensive as this one is.
Question?
You mentioned a couple of times.
There's a microphone on the way here.
You have to all appreciate that I spent a couple of years in the artillery corps. In those days, we didn't know enough to put earplugs in when we fired the artillery. So my hearing is somewhat impaired.
So is mine. You mentioned a couple of times, and when you started out, energy independence, and a couple of timetables, 5 years, 10 years. And you mentioned that some students, freshmen today, by the time they graduate, are you assuming it's a BS or a PhD? serious note, is ambient temperature superconducting on your radar?
Is what?
Room
Ambient temperature,
superconductors.
room temperature superconducting on your radar for solutions to energy independence.
I've read about it and heard some people talk about it, but I don't have enough knowledge to give you an informed answer to that question. And by the way, I did mean bachelor's degree. It's a good thing because Jim and I were at a luncheon today where I asked one of the students how long have they been graduate school? It was 3 years in graduate school. And how much longer do you expect to be? Another 3 years. And Jim corrected her and said, oh, no, you've got to get it done quicker, sooner than that.
How about way over there? Yes. There's a microphone right behind you. There we go.
When do you think we'll be independent from using coal?
That could happen, I think, within the, certainly within the 10-year period I'm talking about. It could even happen by the time the student graduates, but that depends, the second prediction depends on a lot of good things happening, which I can't be so sure of. Coal has the great advantage of being cheaper unless there's a carbon tax. If you put the carbon tax on, coal is one of the most expensive ways we could get energy. But I don't expect to get a carbon tax, so people are going to be evaluating coal by what they pay for it on the market, not by what the cost to our society is. So it's going to be around for a while, but I think within the 10-year time frame I'm talking about, I think it's going to be pretty well out of the picture. We can replace today, we can replace coal-fired plants with natural gas-fired plants without a heavy cost and with a 50% reduction in CO2 emission.
Mm-hmm. Troy?
By the way, I grew up in western Pennsylvania, and towns around me had names like New Mine, and I mean, my grandfather worked in a coal mine for a while. I have a lot of reasons for being unhappy with coal. It's not just an ecological problem. The problem of people who work in the coal, that's one of the most terrible jobs I can think of. If any of you are old enough to have seen How Green Is My Valley, you got some picture, I think an accurate picture of what coal mine life was like.
Mm-hmm. Troy?
Well, solar power has a diurnal clock, right? Night and day. Right. There are other energy sources which are natural, like geothermal, right?
Yeah.
And so where does that fit into what you think? I mean, it's got a long window
Yeah.
there, but
I think it definitely fits in. I do not think there are enough geothermal sources that can be economically tapped to have more than a few percent effect on the total generation of electricity. I could be proven wrong on that, but I think it plays a positive and important niche role.
you have to get below 3,000 feet before you broaden the spectrum.
Yeah, well, the cost issue is how far you might have to drill and where it's located for the drilling, which would generally not near population sources.
But he has unlimited solar.
If you go down deep enough, you got it all, yeah.
Right. All right. Time for a couple more.
Hi. I'm actually a freshman, and so I'm excited for another 4 years.
Check on this man in 3 years from now.
Right.
But so I'm from North Dakota, and so fracking is something that I'm familiar with. And there's some concern over there that the environmental repercussions of fracking, for example, the sediment getting into water tables, and that sort of stuff. What's your opinion on that?
Yeah, I not only have an opinion about it, I wrote a report on that subject. And the report said that there are significantly, potentially important environmental problems. But we know what they are and we know how to solve them, that is, prevent them from becoming problems. But that requires the companies taking responsibility to drill properly and expect what they're doing, and it takes government regulation to be sure that that happens. And I'm a little uneasy about both of those points.
Over there. There's a microphone coming. Here we go.
Can you just comment on energy distribution infrastructure, our aging infrastructure, electrical transmission, and of course gas pipelines, as we're so aware of here in our area?
I think President Obama missed a real opportunity 4.5 years ago when he had these stimulus funds coming out. One of the things we could have been doing in that stimulus fund was starting to rebuild our electrical infrastructure, which is aging, and One of the consequences of its aging is that it's less efficient than it could be. So that's a real opportunity. It's a very expensive undertaking, very expensive, but it would have been a wonderful source of using those billions of dollars we spent in the stimulus funds. It did not happen, though.
Mm-hmm. One more question from anyone? Right here.
Dr. Perry, this is beyond the scope of your lecture, which was excellent, on energy, but you did mention early on the group you're associated with to try to bring down to the end of nuclear weapons around the world. If I'm not mistaken, your associates are Messrs. Schultz, Kissinger, and Nunn. Could you spend just maybe a couple of minutes?
And Sid Drill, who's right
as
here
an
at Stanford.
overview, give us an overview on where that situation is.
The last question is always the hardest.
Right.
I mean, it's mother's milk for me, but it's hard to give a really short answer to that question. I'll try, though. We have, when Schultz and Kissinger and Nunn and I wrote that op-ed, we wrote it because we believed that nuclear weapons posed the greatest danger to the world than any other thing. Either not the way it was in the Cold War, when nuclear exchange between the Soviet Union and the United States, but two relatively new problems that have come up. One of them being nuclear terrorism, and the other being a regional nuclear war, for example, between India and Pakistan. Those dangers are real, and they are grave, and they are largely not understood by the public. So the public is disinterested in them, and as a consequence, the Congress is not willing to do anything about them. To add to that problem, we are on the verge of beginning a new Cold War with Russia. The relations between Russia and the United States are at an all-time low since about 1985. So, during the Cold War, they were better in 85 and 86 than they are today. A long explanation why that's so, but I'm not going to go into that, but they are. Russia is today developing 4 different new families of nuclear-based ICBMs, 4 new ICBMs, plus re-energizing the submarine-launched ballistic missile program. And stating publicly that because they have so many enemies and because their conventional forces are so weak, which they are, that this is their only way for security, to build more and better nuclear weapons. So the trend to decreasing nuclear weapons, with which Russia was cooperating when I was Secretary of Defense, has now gone away, and they're moving in the opposite direction. When I was Secretary, we presided over 4 countries going non-nuclear. If you look at a chart of number of countries with nuclear weapons, it goes up till 1994, and then goes down 4 countries. First time that ever happened. It's starting to go up again now with North Korea getting in the act, and maybe one more if Iran gets a nuclear weapon. And secondly, we dismantled about 8,000 nuclear weapons. Now, that's the good news. The bad news is we still have about 20,000, we and Russia and so on. So it's still a very big problem. And when Schultz and Kissinger and Nunn and Tidwell and I got together on this, our belief was we had stopped doing anything about it. We stopped caring about it. The last really major thing that happened was when dismantling those 8,000 nuclear weapons. So we wrote the op-ed in the hope of waking people up about the problem. And for a while, it seemed to be going fine. I mean, groups like ours are formed all over the world now. There are gangs of 4 in Germany and in Italy and in the United Kingdom and Norway, Japan, Australia, even in Russia. But unofficial people like myself and the other people in our groups don't make government policy. We try to influence it. And by about 2006, it was clear that we were not influencing successfully. So we got these groups going. The first really big thing that happened on a governmental basis happened 2 months after President Obama was inaugurated, when he gave a speech in Prague. In that speech, he says, "I state clearly and with conviction the commitment of the United States to seek the peace and security of a world without nuclear weapons." I can still remember how thrilled I was when I heard that. I could hardly believe it. And for a couple of years, we made a lot of progress. We had a treaty with Russia called the New START, which reduced the number of nuclear weapons, but more importantly, had the United States and Russia on a dialogue on nuclear weapons. We had the United Nations make a resolution in favor of reducing and eliminating nuclear weapons. Most importantly, I think, we held a nuclear summit meeting, first in Washington, then a second follow-on in Seoul, and then a third one coming up next year in Amsterdam, for the purpose of getting the nations to take more seriously the control of fissile material. Because if a terrorist cannot make a nuclear bomb from scratch, but if he has the fissile material, he can make it. And what we call an improvised nuclear bomb, crude improvised nuclear bomb, it is improvised, it is crude, but it goes off with the same bang as the Hiroshima bomb. So one of those set in San Francisco or Washington or New York would kill hundreds of thousands of people. And more importantly, even more importantly than that, it would create a social, economic, and political chaos in the country. I've just finished writing a book, and in fact, my daughter was the editor of that book, in which I lay out these dangers. I start the book with a hypothetical scenario. The scenario is a terrorist, and I describe how it happens, gets a bomb, gets the fissile material, makes the bomb, delivers it in a freight plane to New York City, and then gets a truck and takes it into the middle of New York City and sets it off. Pardon me, Washington, and sets it off. And in my scenario, the Congress was in session at the time. The Chief of Staff and the Secretary of Defense were testifying to the Congress at the time. The Vice President was there at the time. The Congress was obliterated. The White House was obliterated. 100,000 people died instantly, and the government was gone. And again, in the scenario I had, the presidency evolved to the President pro tem of the Senate, who at the time was in the Mayo Clinic undergoing treatment for prostate cancer. And just try to imagine the chaos. And the other part of the story was that the terrorist who dropped it sent a message taking credit. He said, by the way, I have bombs planted in 5 other cities, and they're going to go off a week. Can you imagine what would happen in all of the cities in the United States? People would stream out of them. The government would just come to a complete stop. So the social impact and the political impact are almost worse than the fatalities that result from it. Nobody understands that scenario is a real live scenario. It could happen, and it's not a remote possibility. So I'm getting excited about this problem. We are doing everything we can with the immediate goal. The most important goal is to ensure that nuclear weapons are never again used. But it's really an uphill battle. It's primarily an uphill battle because the American people do not understand what the danger is, and therefore their Congress is unwilling to act on it. And thank you. It's great to talk to you tonight. Yeah.
Is an engineering hero, and we're going to present to you, you can let it sit here for the moment, but this is a copy of the plaque which is on the wall just outside to the right, where we have wall plaques of all of the engineering heroes. So please join me in welcoming the latest engineering hero, Bill Perry.
Can you hear me in the back? I really feel a little sheepish standing up here because while I have 2 degrees from Stanford, I never took an engineering course here. But all of my degrees are in fact in mathematics. But as soon as I graduated, as soon as I got my PhD, I went to work for an electronics company and stayed there for about 10 years and then founded my own electronic company and left there only to become the Director of Defense Research and Engineering, which was sort of being the chief engineer of the country. So I think that maybe makes me feel all right about standing up here in this engineering environment. Most of my time, as Jim has suggested, has been spent working trying to reduce the danger of nuclear weapons, and in particular, doing everything I can to ensure that a nuclear weapon is never, ever used again. And most of my talks, in fact, are on that subject. But I decided to deviate from that tonight. First of all, it is a depressing subject, really, and I get depressed sometimes talking about it, as important as...
Well, he's really spent a career kind of straddling industry and government, and after he completed his PhD at Penn State, he took a job in the defense industry and was also a technical advisor to the Defense Department. So the story he tells about this is that in one day in the fall of 1962, he got a call to go to Washington to consult on what was described as an urgent technical problem. So when he arrived, apparently he was shown some pictures of some Soviet missiles being deployed in Cuba. And I think this was really a stark introduction to some of the geopolitical problems that Bill spent much of his career on later. In 1977, he became Undersecretary of Defense for Research and Engineering under Jimmy Carter, and after that term, after Carter's term, he returned to the Bay Area, but stayed very active in national politics. He returned to Washington as Secretary of Defense in 1994. One of the hallmarks, I think, of Bill's tenure as Secretary of Defense was that he did what he could to reduce the Cold War's deadly legacy of nuclear weapons. And in 2007, he took a really dramatic step by joining forces with former Secretaries of State George Shultz and Henry Kissinger and former Senator Sam Nunn to publicly call the world's attention to the grave danger posed by nuclear weapons. And he's been a tireless campaigner for this cause since that time, well, in fact, for all of his career. So in addition to his many honors, he's a member of the National Academy of Engineering, the American Academy of Arts and Sciences, and he's been recognized for distinguished services by almost every agency associated with the Department of Defense, NASA, and so on. And he's even, in 1988, was named a Knight Commander of the British Empire. So tonight, Bill, we celebrate you as in each in their own way change the world. So unlike many award events, we actually ask the people that we're honoring how they would like to spend some time at Stanford and try and set up a day or an evening or an afternoon that would really be special and meaningful to them. And Bill spent this afternoon, first he and I had lunch together with some engineering PhD students, and he spent the afternoon touring some engineering labs and seeing some of the interesting research going on, particularly I think in the area of energy, which is going to be a highlight of his talk this evening. So as all of you know, Bill is best known as the nation's 19th Secretary of Defense. He served under President Bill Clinton between 1994 and 1997. But he's also really widely recognized as a longtime advocate for the need to reduce the danger of nuclear weapons. And I think some of this traces back to the time when Bill was in the Army Corps of Engineers, and he served in the Army of Occupation in Japan, where he saw firsthand the devastating effects of nuclear war. He's one of those unique people whose career has spanned public service, business, and academia. And if you look through his career, you will see him actually moving from one to the other and then back and forth through the time that he's spent in Washington, at universities, and in industry. He's been decorated by more than a dozen countries for his work, including the U.S. Presidential Medal of Freedom. Bill is currently an emeritus professor in our Department of Management, Science, and Engineering and a senior fellow at the Freeman Spogli Institute. But his association with Stanford actually started more than 60 years ago when he got a bachelor's and a master's degree here in mathematics. And then he returned back here in 1989 as a faculty member. So as I said a moment ago, well, good evening and welcome. I'm Jim Plummer, the Dean of the Engineering School, and we're here this evening to honor Bill Perry, who's a former U.S. Secretary of Defense and Professor Emeritus in our Management Science and Engineering Department. We're also delighted that Bill's wife, Lee, is with us, and Bill's daughter, Robin, are with us as well to celebrate this evening. Not only do we have a packed house here in the video auditorium, but there literally are hundreds of Stanford alums who are watching the live webcast of this event over the internet. The Stanford Engineering Heroes program is 3 years old now, and we set this program up to recognize the achievement of Stanford-affiliated people, faculty, graduates, and so on, who have profoundly changed and advanced the course of human, social, and economic progress through using engineering. Our engineering heroes really embody all that the School of Engineering stands for. The school stands for innovation, it stands for entrepreneurship, for leadership, and for world-class teaching and research. And as we hear from our heroes from time to time, they are the people who have really changed the world using these attributes. This year's heroes, in addition to Bill, include Jerry Yang and David Filo, who were the founders of Yahoo, John Bloom, who was one of the earthquake pioneers, and Marty Hellman, who was one of the people who invented public key cryptography. And these inductees this year include a distinguished group of inductees from the last couple of years, people like Fred Terman and Bill Hewlett, Dave Packard, and Vince Cerf. So it's a very distinguished group of people who have been affiliated with the engineering school and who really have...
It is. And I wanted to have a more hopeful talk tonight and decided to talk about energy, which is a very important subject in which we have made remarkable progress, primarily because of technology developments, many of them happening right here at Stanford. I have tied the subject of security. My title is Energy, Technology, and Security. So why do I tie it to security? Every American president, going all the way back to Dwight Eisenhower, have stated that an increased dependence on foreign oil threatens our security. Every president promised to break that dependence. Eisenhower said that if more than 20% of our oil had to be imported, it would endanger our security. President Nixon promised energy independence by 1980, which is some time ago, you know. Carter called energy crisis the moral equivalent of war. Clinton said that energy is the key to our national security. And President Bush, the second President Bush, lamented America's addiction to oil. So when I say that this is a security problem, I'm in good company. All of these presidents have said that. There's been a bipartisan consensus for these last 60 years to reduce our dependence on foreign oil. Well, all presidents for the last 60 years have promised to do so. How well have they done on their promises? Just two figures to put into perspective. In 1970, our oil imports were $3 billion.